Hi, my name is Nikita Leppenen. I'm a PhD student at Weizmann Institute. I work in a collective quantum optics group led by Dr. Efi Shahmoon. And today I'm going to talk about different kinds of decay in quantum open system and how this could be. Okay. Okay. Thank you. About different kinds of decay, like this, in optics, in collective systems and in quantum open system, and how they could be used to study quantum computers, and also how quantum computers could be used to study such kind of systems. So nowadays, quantum computers, I mean, sorry, how? Okay. I mean, quantum computers nowadays are used to run some quantum algorithm or used to simulate some quantum many-body problem. And such kind of devices, we usually think about unitary evolution, Hamiltonian evolution as good guys that help us to generate some gates, entanglement, and about dissipation as a bad guy that causes errors. By dissipation, I mean different kind of incoherent laws like energy relaxation time, different decays, and something like that. But from like quantum many-body, quantum optics point of view, I think about dissipation not only as a like bad guy source of errors, but also as a good guy that could be used to generate something something good, for example, entanglement. And on the other hand, maybe I'm thinking about NISQ devices as a perfect devices to simulate my noise. And I'm going to talk about it today. So by open quantum system, generally, I mean that there is a system or maybe several systems that do interact between each other, not necessarily Hamiltonian way, but also due to the dissipation to the common collective environment. They also could dissipate to different environment uh, and so on. In quantum optics, our system is, okay, you don't see it here, is ensemble of atoms. And, okay, sorry, this is atoms. You see it by gray balls. This is ensemble of atoms, and they do interact with photonic modes. And there are several, like, infinite amount of photonic modes, and they could interact with the same mode. They could decay atoms into some common direction. They could decay atoms to different photonic modes. They could interact between each other due to the fact that they decay atoms to decay photons to each other. And generally, even for two-level atoms, it's a complicated problem, but on the same time relevant problem for many physical, chemical, biological system, and also it could be used as a system to test some novel quantum many-body non-equilibrium phase theories. Okay, so first let me start to discuss the case, the most simpler case where there is system coupled because of all of my atoms, for example, decay to the common reservoir. So in optics view, there is a decay model when all the atoms are coupled identically to the same field. In realization, you can think about atoms in a cavity that all sits in the antinodes, so they feel in antinodes of the cavity, so they feel identical field. And that's why I could not understand from which atom, if I detected the light outside the cavity, I don't know which atom emitted photon. So we can, all my system then describe by symmetric superposition of these atoms. And this is like, I consider it as a huge spin. And let's study how this spin will scatter light. So I assume that they all initially in the ground state, and I shine my laser, and I have dissipation. So After some long time, the system will saturate to its steady state. And if there are no lasers, so I will show you the plots for magnetization. If there are no laser and all the atoms are in the ground state, that my magnetization is -1. And if there is a laser and is really strong, much stronger than dissipation, then my magnetization is 0 because there is strong gravity oscillation much faster than the decay. And so the atoms with equal probability in excited states or in the ground state. And in between, I do have second order phase transition. And it was studied in our group that the atomic state before the phase transition is actually a pure state and entangled state. And the entanglement is proved by calculation of spin squeezing. So I showed you that I have dissipative system, but still in dissipative system I could gain some entanglement. So now what happens if I do have not only collective dissipation to the same environment, but also some local dissipation. And when about quantum circuits, you can think that I have some errors on each qubit. And in the cavity setup, you can think that you have not only decay along the cavity axis, but also decay to different modes outside the cavity. In real cavities, this relation between this decay depends on called cooperativity. So in that case, I'm showing you here mean field study, the easiest one. Again, the magnetization is between -1 and 0, but there is a region where I do have two stable steady state. It means depending on my initial condition, I do saturate either to one or to another one. We went a little bit further. We did full quantum solution of that problem, and we found that the full steady state of such system is a bimodal state, has bimodal distribution, which means that this steady state is incoherent superposition of two quantum states. To find these quantum states, we used Liouvillean theory, Liouvillean gap, if someone is familiar with that. So we found these two states, and we found that the steady state consists of two states, and one state is almost totally mixed state. This is a state that doesn't have any entanglement, and that's the state where you have a lot of local dissipation. But another state in this superposition is almost pure, and it has good squeezing, so it means entangled states, and also it has huge fidelity with coherently radiating spin states I showed you before, that states when I do have only pure decay. So it all on the steady state after the long time. So generally, if you think about time dynamics and imagine if your collective effects are strong, you can think that, of course, you will have this collective physics as long as you local dissipation doesn't play a role. So you will see the collective physics until the first local event. And this is what you usually expect from NISQ devices, because just do your algorithm before you will have any decay, before you will have any local dissipation. But what we found in this work, and this is surprising here, I'm showing you this simulation with quantum trajectory of single realization of the system, that in the steady state after the long time, I see quantum switching between mixed state, which is not a good state, and my CRSS state, which is collective states with entanglement. So, okay, I've shown you two examples of quantum optics setups that we study, cavity and cavity with individual decay. So actually pretty simple examples, because even where I do have collective and individual, I still can find which one is which. But generally, if I want to study decay from some atoms, put it in free space, in atomic array, or different configurations, there is not easy to distinguish between two of them. And the Hilbert space is actually exponentially growing, because even for two-level atoms, the 2 in the power of n, so computationally you can reach it only with n up to 20 or something. So probably studying it on quantum computer could give an advantage. And if there is quantum computer, noisy quantum computer, you can consider like this noise as a local noise, as I showed you before. And for the collective noise, we can think about the following. So how do you couple two qubits to, or two atoms to some environment, some shared environment? You can do it through the ancillary qubit. So this is simply how we do this in optics. So you don't couple two qubits just by gate. You couple two of them to the same ancillary qubit. It's like you put two atoms in a cavity, different coupling, and then you start to weakly measure this qubit, and so that's how you get the dipole-dipole incoherent interaction between two atoms. So that's pretty much all. I just wanted to say that we can bridge the gap between quantum optics system and quantum computers. On the one hand, I showed you that you can use some ideas from quantum open system, for example, that you can create entanglement through the dissipation, and also that if you even have local noise, you can still hope to find some entanglement. But on the other hand, I showed you a possible problem that is relevant and could be realized on a quantum computer. And if you ever be in Weizmann, you can find our room by this picture on the door. So thank you.